In this video, we're going to look at some examples of using the ratio test to determine whether certain series converge or diverge. We quickly recall the ratio test. For the ratio test, we're going to be looking at a series from n equal 1 to infinity of a sub n where we have non-zero terms. We're going to compute the number r, which is defined to be the limit as n approaches infinity of the absolute value of the ratio of two consecutive terms. Namely, we're going to take the n plus first term, a sub n plus 1, and divide it by the previous term in our series, a sub n. The value for r will then determine what happens with our series. If our limit r is less than 1, then the series will converge. If our limit r is greater than 1, then our series will diverge. And if our limit is exactly equal to 1, then the test is actually inconclusive. There are examples where the limit will be 1 and the series converges, and there are examples where the limit is 1 and the series diverges. And this means we're going to need to use a different test in order to analyze our series. So maybe use a comparison test or an integral test or some other test other than the ratio test. Since we'll be taking the ratio of two terms of our series to compute the number r, the ratio test is incredibly useful when we have a series whose terms consist of expressions which are exponential, powers, or especially factorials. In our first example, we want to determine whether the series from n equal 1 to infinity of 2 to the n over n factorial converges or diverges. The term of our series here involves an exponential 2 to the n as well as a factorial, and so this is an indication that the ratio test is an appropriate test to try. In order to use the ratio test, we need to compute a sub n and a sub n plus 1. A sub n, of course, will just be our term of our series, 2 to the n over n factorial. And a sub n plus 1 is the next term in our series. And so we can find this by replacing the n in a sub n with n plus 1. So in the numerator, we get 2 to the n plus first power. And in the denominator, we get n plus 1 factorial. It's important to note that in this denominator, this is not the same thing as n factorial plus 1. We need to replace n with n plus 1 first, then take the factorial. Well, once we have these two terms, we can go and we're all set up to compute the number r, which is the limit as n approaches infinity of a sub n plus 1 over a sub n. Notice that we're leaving off the absolute value bars here because all of our series terms are going to be positive. 2 to the n is always positive, and n factorial is always positive. So we can certainly leave the absolute value bars if we'd like, but we can omit them in this case. So now we have the limit as n goes to infinity. We have a sub n plus 1, which we've seen is 2 to the n plus 1 over n plus 1 factorial. And we need to divide this by a sub n, which we can think of as multiplying by the reciprocal. So instead of dividing by 2 to the n over n factorial, we're going to multiply by n factorial over 2 to the n. Now, because we have exponentials and factorials, these things can be simplified quite a bit. 2 to the n plus 1, we can think of as 2 to the n times 2. N plus 1 factorial, we can think of as n plus 1 times n factorial. And then, of course, n factorial over 2 to the n. And now several things here cancel. For example, 2 to the n divided by 2 to the n will give us a 1, as will n factorial over n factorial. And so all of that canceling out, what we're left with is just the limit as n goes to infinity of 2 over n plus 1. And as n goes to infinity, 2 over n plus 1 will get smaller and smaller and get closer and closer to 0. And that limit of 0 is certainly less than 1. And so here we found this number r, this limit of the ratio of consecutive terms. We found this limit was equal to 0, which alone means nothing. The important part is that that number is less than 1. And so our series will be seen to converge. And here it's going to converge by the ratio test since our ratio is less than 1. In this example, we want to determine whether the series from n equal 1 to infinity of negative pi quantity to the n over n to the fourth converges or diverges. The term for this series is an exponential, negative pi to the n, over a power function n to the fourth. And since the ratio test applies nicely when we have terms with expressions involving exponentials and power functions, we'll try to use the ratio test for this example. We know that a sub n will be our given term, negative pi to the n over n to the fourth. And therefore a sub n plus 1, the next term in our sequence, or in our series, will be negative pi to the n plus first power divided by n plus 1 to the fourth power. To use the ratio test, we're going to compute the number r, which is defined to be the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. And here, in this particular series, we can substitute in our two values here. So we have negative pi to the n plus first power divided by n plus 1 to the fourth, multiplied by the reciprocal of a sub n, which would be n to the fourth over negative pi to the n. And so we want to simplify this expression and then compute this limit. Now notice that we can get several things to be simplified here. First, the negative pi can just simply become pi by evaluating the absolute values. And so when we group this, we have in the numerator, we have pi to the n times pi. That's our pi to the n plus 1. That'll be over n plus 1 to the fourth, multiplied by n to the fourth over pi to the n. And here we can cancel out the pi to the n, so we just have a constant of pi in our numerator. And so here we're going to get the limit as n goes to infinity of the constant pi times n over n plus 1 quantity to the fourth power. And so n over n plus 1, as n goes to infinity, this quantity in parentheses will go to 1. And so what we get is a limit of pi times 1 to the fourth power, which of course is just equal to pi. And pi here is approximately 3.14 and is greater than 1. And so here we have a series where the ratio of consecutive terms has a limit that's bigger than 1, and therefore this series diverges by the ratio test because the limit of the ratio of consecutive terms is greater than 1. In this example, we want to determine whether the series from n equal 1 to infinity of negative 1 to the n times n factorial squared over 2n factorial converges or diverges. Because we have multiple factorial expressions in our term for our series, the ratio test is a natural test to try to use in order to determine whether this converges or diverges. For the ratio test, we need our consecutive terms. Here a sub n is our given term, negative 1 to the n times n factorial squared, divided by 2n quantity factorial. When we compute a n plus 1, we do have to be a little bit careful here. We will get negative 1 to the n plus first power. In the numerator for our factorial, we're going to have n plus 1 factorial, quantity squared. So notice that we do need an n plus 1 factorial, not n factorial plus 1. And in our denominator, we're going to have 2 times n plus 1 factorial. Again, notice here that the order of the operations are important. In our original denominator, we're first multiplying n by 2 and then taking the factorial. And so in a sub n plus 1, we first have to multiply n plus 1 by 2 and then take the factorial. And of course, this can be simplified a little bit. Negative 1 to the n plus 1 multiplied by n plus 1 factorial squared. And in our denominator, 2 times n plus 1 is going to be 2n plus 2 factorial. And so this will be the formula that we use for an plus 1 in terms of computing our limit. So the value for r for this particular series will be the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. A sub n plus 1, as we just saw, was negative 1 to the n plus 1, multiplied by n plus 1 factorial squared. And here, instead of having the squared expression, I'm just going to write that as n plus 1 factorial times n plus 1 factorial. Of course, this is the same thing, but it will make it easier to simplify in the next step. In the denominator, we saw that we have 2n plus 2 factorial. And so this is our expression for a sub n plus 1. We then have to divide this by the expression for a sub n, which means we can multiply by the reciprocal, which is 2n factorial divided by negative 1 to the n, times n factorial squared, which we can write as n factorial times n factorial. And so this is the expression that we want to simplify here in the absolute value and then take the limit of. So we have the limit as n goes to infinity. The absolute value will simplify with the negative 1 to the various powers. And so what we're left with is an n plus 1 factorial in our numerator, which we can think of as n plus 1 times n factorial times n plus 1 times n factorial, all over 2n plus 2 times 2n plus 1 times 2n factorial. So this is our standard way of simplifying factorials. And the reason we simplify them like this is because we're going to be multiplying this by the 2n factorial over n factorial times n factorial. And now we have lots of cancellations. In fact, all of the factorial terms cancel out completely. We have an n factorial in the numerator and 1 in the denominator. We have another n factorial in the numerator and another in the denominator. And we have a 2n factorial in both numerator and denominator. And all of those factorial terms cancel out. And what we're left with is the limit as n goes to infinity of n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1. And so we have to compute the limit of this rational function here. And if we wanted to, we could go ahead and work all of this out. So this will be n squared plus 2n plus 1 in our numerator. We'll get 4n squared plus 6n plus 2 in our denominator. Since we have the largest power of n being n squared in the denominator, we can multiply this by 1 over n squared divided by 1 over n squared. This will give us then the limit as n goes to infinity of 1 plus 2 over n plus 1 over n squared all over 4 plus 6 over n plus 2 over n squared. All of these terms with an n in the denominator will then go to 0 when we take our limit as n goes to infinity. And what we're left with is the value 1/4, which we know to be less than 1. And so through all of this simplification and limit evaluation, what we see is we get a value of r, which is 1/4 less than 1. And by the ratio test, this particular series converges. So we have a series that converges by the ratio test. If you'd like to try some problems on your own, you can pause the video and determine whether the following series converge or diverge. You can resume the video in a few seconds to see the full solution. The first series is the series from n equal 1 to infinity of n cubed over 3 to the n. And the second series is the series from n equal 1 to infinity of n plus 1 quantity factorial over 2n. For the first series, we have a sub n equaling n cubed over 3 to the n, and a sub n plus 1 equaling n plus 1 quantity cubed over 3 to the n plus 1. The value of r is then the limit as n approaches infinity of the ratio of these two terms, which would be n plus 1 cubed over 3 to the n plus 1, multiplied by 3 to the n over n cubed. The 3 to the n plus 1 term in the denominator can be rewritten as 3 to the n times 3, and the 3n's will then cancel out. We can then rewrite n plus 1 cubed over n cubed as n plus 1 over n quantity cubed. As we take the limit as n goes to infinity, the expression in the parentheses, n plus 1 over n, will get closer to 1. And so this approaches 1/3 times 1 cubed. And of course, 1 cubed is just 1. And so a limiting value here, our value of r is 1/3, which is less than 1. And since r is less than 1, this particular series converges by the ratio test. For our second example, we have a sub n equaling n plus 1 factorial over 2 to the n, and therefore a sub n plus 1 will equal n plus 2 factorial over 2 to the n plus 1. Notice that in the numerator, we would actually have n plus 1 factorial, and of course that can be simplified to n plus 2 factorial. We then compute the value r, which is the limit as n approaches infinity of a sub n plus 1 over a sub n. Here we have n plus 2 factorial over 2 to the n plus 1, multiplied by the reciprocal of a sub n, 2 to the n over n plus 1 factorial. We can rewrite n plus 2 factorial as n plus 2 times n plus 1 factorial, and we can rewrite 2 to the n plus 1 as 2 to the n times 2. We can then cancel the 2 to the n's and the n plus 1 factorials, and we're left with the limit as n approaches infinity of n plus 2 over 2. This is a limit that diverges to positive infinity since we have an n plus 2 in the numerator, which will get large, and a constant of 2 in the denominator. Since infinity is certainly greater than 1, this limit is bigger than 1, we conclude that our series diverges by the ratio test.